Hello students, welcome to the class. In today's class, I will continue from the last lecture, that is lecture number 2. Okay, and we will solve 5 more numericals today. Okay, so the question number 11 is the electric field at a point on equatorial line of a dipole dash to direction of dipole moment. So you have to tell what is the direction of electric field at a point on equatorial line, how it is related to dipole moment of the electric dipole. Okay, let's see out of these 4 options which one is correct. Okay, we know a electric dipole consists of two equal and opposite charges. Let's say this is minus q here and this is plus q here, and you know the direction of electric dipole moment of an electric dipole is always directed, you know, from negative charge to positive charge, right? So this is the direction of dipole moment of electric dipole. Okay, and what is equatorial line? Equatorial line is the perpendicular bisector of any line, okay, of this electric dipole. So perpendicular bisector means, let's say this is of length 2l. If this is the length 2l, then if it is the length l, up to this the length is l, then this is the perpendicular bisector, and perpendicular bisector means this thing, and this is known as equatorial line. You know, right? This is known as equatorial line. And let's say I want to find electric field at that point P, or let's say not P, let's say R, any point. We want to find electric field at that point R. This is the equatorial line. Okay, then what will be the electric field? And if I put a test charge Q naught, then it will feel a force in this direction, right? It will attract, minus q will attract an electric field due to minus q, let's say E1, then it will be in this direction, E1. This will be in that direction. And due to that plus charge plus q, this q naught will experience a force in this direction, like it will repel this one, and electric field will be in this direction, E2 will be in this direction. Now if you complete the parallelogram, because this length and this length will be same, because minus q and plus q have the same magnitude. So now if I want to find the resultant, then the resultant will be in this direction. This is the resultant E, the resultant electric field E, and I can write this electric field is due to E1 and E2. And if you see the direction of this resultant electric field, this is in opposite to the direction of electric dipole moment. So which option is correct? Of course, option B is a correct option. Okay, let's move to the next question. Okay, the question number 12 is the electric field intensity just sufficient to balance the Earth's gravitational attraction on an electron will be, you have to tell out of these 4 options which one is correct. And you are given the mass of electron is 9.1 10 to the power minus 31 kg, and charge of electron is 1.6 10 to the power minus 19 coulomb. This question is really simple, right? If you take an electron, if you place it here and at a certain height from the ground, let's say at a height h, then it will be attracted towards the center of the earth with a force equal to its weight, right, mg, with a force equal to mg. With this force it will be attracted towards the center of that. Mg means mass of the electron times g. Now if I can provide the same force, exact equal amount of force in upward direction, then it will be suspended in air, right? It will be suspended in air, it will be balanced in that air. Now I can provide the same exact amount of force mg by applying electric field, and we know for electric field the electron will experience a force equal to the electric field intensity times the charge of electron, right? Then if the force due to electric field is acting in upward direction and this mg is acting in downward direction, and if these two forces are of equal magnitude, then this electron will be suspended in air, it will remain balanced in air. Okay, so it is fairly simple. And let's say it is experiencing a force capital E small e in upward direction, then of course if EE equal to mg, then it will be balanced in air, or this electric field will be mg divided by E. This m is mass of electron, mind this mass of electron. Then just put the values. Mass of electron is 9.1 10 to the power minus 31, and G is let's say 9.8, and electric field the charge of electron is 1.6 10 to the power minus 19. If you solve it, I have solved it. If you will find, the answer is 5.6 10 to the power minus 11 Newton per Coulomb. So the option A is a correct option. Okay. Okay. Let's move to the next question. The question number 13 is, if the electric field strength of a short dipole at a point on its axial line is 5 into 10 to the power minus 10 Newton per Coulomb, then on the equatorial line at the same distance, the electric field strength will be, out of this 4 options, which one is correct? You have to choose. Okay. So what we know? We know the electric field strength at a distance, at a certain distance on its axial line is equal to the twice of the same distance on its equatorial line. We know that, right? I mean to say, if this is my dipole, minus q plus q, and this is the center, if this is the center of the dipole, then if it is at that point, let's say it is at the point P, and this length is, let's say, some x, and if it is at the same distance, let's say this is another point P dash, and it is at the same distance x, then you understood, right? From the midpoint, let's say midpoint is O. If OP and this is OP dash, if these are at the same distance x, then electric field at the position P will be nothing but just twice the electric field at the position P dash. This is what I mean to say. Then this is simple, right? The question is simple. What you are given, see, if the electric field strength of a short dipole at a point on its axial line is given. Axial line is given means EP is given. You are given EP. EP equal to how much? 5 into 10 to the power minus 10. Then what will be EP dash? EP dash will be EP by 2. That is 5 by 2. That is 2.5 into 10 to the power minus 10 Newton per Coulomb. Then which option is correct? Option A is a correct option. Right? Okay. Let's move to the next question. Okay. The question number 14 is, which of the following graph shows the correct variation on magnitude of torque on an electric dipole rotated in uniform electric field from stable equilibrium to unstable equilibrium? So first of all, you have to understand what is stable equilibrium and what is unstable equilibrium. First of all, let me explain what is stable equilibrium and what is unstable equilibrium. Okay? Let's say this is the direction of electric field. Let's say this is the direction of electric field, and you have placed an electric dipole. Let's say this is P, electric dipole P, from minus to plus charge. Okay, let's say this is the electric dipole P, and let's say this is making an angle theta. Okay, what we know, the torque is nothing but PE sin theta. The torque experience is PE sin theta, or if you write in vector notation, that is P cross E, right? If you tau equal to P cross E, if you write in vector notation, it is a cross product of P and T. I am not writing the cross product. I want to make you understand in terms of the angle, because the question is variation of tau with angle. So we can see the variation of tau with angle, right? And what is that angle? This is the angle between P and E, dipole moment and electric field. Okay. Now see, if P is aligned along the direction of electric field, if P is aligned along the direction of electric field, then we know theta equal to 0, right? Then what will happen? Torque acting on that electric dipole will be 0. If theta is 0, then tau is 0. When it is the case, when P is along the direction of electric field, and this is known as stable equilibrium position. Stable equilibrium. This is stable equilibrium. Why it is known as stable equilibrium? Because the electric dipole is stable when it is along the direction of electric field. When it is along the direction of electric field and you disturb it from its position, then it will try to come to its original position. That is, it will try to align along the direction of electric field. Okay, that is why it is known as stable equilibrium position. Another case, if theta equal to 180 degree, you see, then also tau equal to 0, right? If theta equal to 180 degree, then also tau equal to 0, because sine 180 is 0. It is the case when the electric field and the electric dipole are in opposite direction. When the electric field and dipole are opposite in direction, then also the torque acting on this electric dipole is 0. And this is the condition of unstable equilibrium. This is unstable. Why it is unstable? Why it is not unstable? Because when it is along the when it is in opposite to the direction of electric field and you disturb it from its position, then what it will try? It will not try to regain its original direction. It will not go, means if it is in that direction, you disturb it, it will not try to go in opposite direction. It will just switch its direction and it will try to come to stable equilibrium configuration. That's why this configuration is known as unstable equilibrium configuration. And if you see, at theta equal to 0, tau equal to 0, at theta equal to 0, tau equal to 0, at theta equal to 180, tau equal to 0. But when it has some theta value, then it will experience some torque. And you can understand, right? If it is in the direction of electric field, it is not experiencing any force, and it will rotating, then it will feel some torque. And when it is 90 degree, then it will feel maximum torque. Why it is feel maximum torque? Because sine 90 is 1, and you know the maximum value for sine is 1. Then at perpendicular to the field, the electric dipole will feel maximum torque. And again, when it will rotate, and theta value increases more than 90 degree, then it will again feel less torque. And finally, when it will be anti-parallel to the direction of electric field, it will not feel any torque, right? So you can simply understand what is the behavior of the graph. The behavior of the graphic like A. When theta equal to 0, it will not experience any torque. When it is 90 degree, it will feel maximum torque, and when it is 180 degree, it will not feel any torque. This is known as stable equilibrium configuration. This is unstable. This is the unstable position. This is the stable position. This is the unstable position. But in both the positions, it will feel zero torque. Okay. Okay. Let's move to the next question. Question number 15 is, the electric field intensity due to a dipole of length 10 cm and having a charge 500 microcoulomb at a point on its axis at a distance 20 cm from one of the charges is what? You have to tell out of this 4 options which one is correct. So we know if a dipole consists of minus q plus q and a point P at a distance x from the midpoint of this dipole is x, then we know electric field at the point P is nothing but 1 by 4 pi epsilon naught 2 times P times x divided by x square minus L square whole square, where P is nothing but electric dipole moment. Then we can write 1 by 4 pi epsilon naught 2 times P. P is electric dipole moment, which is q times length x divided by x square minus L square whole square. Here 2L equal to, given this is 10 centimeter, or we can write 0.1 meter. Then what will be L? L will be 0.05 meter. Then what will be x? X will be this length, that is L, plus this distance, and this distance you are given. This is given as C, 20 centimeter from one of the charges. That is, this will be L plus 20 centimeter. If you convert it into meter, then it will be 0.2 meter, or L equal to 0.5. This is 2.2. Then it will be 0.25 meter. Now put the values of L and x here. Then if you solve it, if you put the values of q equal to 500 microcoulomb L equal to 0.05, x equal to 0.25, then if you solve it, you will find the answer is 3.8 10 to the power 6 Newton per Coulomb. Just plug in the values of L and x. You know, then you will find 3.8 10 to the power 6 Newton per Coulomb. That is option A is a correct option. Okay, that's it for today. We'll meet you in the next class. I will meet you in the next class.